Dear learners, welcome to week 8 and this is our 4th lecture. In this lecture, I shall explain something about the advanced material. Till 8 week lecture 3, I have completed the shell theories and I have covered 2-dimensional solutions as well as 3-dimensional solutions that is valid for composite cells. But as you are aware that these days if you design a shell structures for aerospace application or sometimes you may be heard or idea about a smart structures, means when a composite laminated structures are integrated with the smart materials like piezoelectric materials or any magnetodestructive materials or shape memory alloys, then these structures are known as smart structures. So, besides their original, or I would like to say that structural function, they also help us to control the vibration or sometimes we want to know the deflection or the desired function can be done with the help of these smart materials. So, in this lecture I shall explain that how do we develop this mathematical models for, let us say, a composite shell having some piezoelectric layer over it. So, before that I will explain the application of these smart structures. So, smart structures have extensively, I would like to say, that used in lightweight and ultra reliable structures, so aerospace, naval structures, automobile and space technology. And we need a high performance or a multifunctional, as I have said in the opening of this lecture, that we need one more extra functional this thing, like if we have only structural, okay, composites are very good that they give tailorable properties and we are able to design a lightweight structure. Besides that structural performance, they are able to do one more task, that is like able to control, able to sense, so that known as multifunctional. So, when these structures are integrated with some smart materials, then these are known as smart structures. Multifunctional structures, already said that active vibration control, shape control, health monitoring, seismic control and self repairing ability. So, when the structure have this kind of any one, it may have or it may have all the functions depending upon the requirement, then these structures need to be analyzed or a mathematical model. The question comes up here, as we know that composite material is a orthotropic material, similarly the piezoelectric material or the magnetostructive materials are orthotropic in nature and the behavior becomes more complex because now we have a electrical and mechanical field coupling. So, what are the good point for this, or I would like to say that advantages of this smart structure? These are having high specific strength, stiffness, easy tailorability, low maintenance cost, long lifespans, good durability. The weak points are that high material cost and debonding and peel off take place at the interfaces. That is the most important reason. That is why we are not means the complete or it is not allows that complete application in the different field. Then the lack of material, that we are not having idea about the long term behavior. So, like fatigue, fracture, that how it will behave in the long term durations. So, at the interfaces there is a strong inhomogeneities occurs, like sharp material discontinuities, sometimes geometric discontinuities. So, this causes a large out of plane stresses at the interfaces and also exhibit the edge effects. Sometimes it is also known as corner effects for different sport conditions. And these issues becomes more complex for hybrid. Now I am coining a term hybrid. Hybrid term is used when we integrate a composite laminates with the piezoelectric layer. So sometimes we called it a smart structure or a hybrid laminates, and then may lead to premature interlaminar failures, or if we talk about in the terms of sensing and actuations, they may lead to complete loss of actuations or sensing authority of the piezoelectric layers. So first of all, we must know what is the piezoelectricity. So the word here piezo means pressure, electricity means electricity. So electricity is produced due to the pressure. So this is the effect which was discovered by Pierre and Jacques Curie in 1880, and so they have discovered that in a quartz crystal, if you apply a pressure across the thickness, then electrical voltage or current is generated. And there is a vice versa also, if you applied a electrical field, then there the material get expand or contract. So this effect was discovered. So initially it was discovered some natural material, then there were some other like sugar cane, quartz, crystal, Rochley salt. See, in this all they have discovered that this effect exists, and most surprisingly even human body, human bones or bones have this piezoelectricity effect. So after, I think I would like to say that a real application in the structural point of view have started in 1985. The first work was Crowley and Lewis, has they have ultrasonic sensor, so sonar devices for underwater applications. So this effect was used, and later on that man-made piezoelectric materials were developed, or I would like to say that polymeric piezoelectric materials were developed. So in this field, from that starting in the 2000, that review articles were presented, and in these articles that various works which were done by different researchers have been cited. Yes, there are number of books are also available on this topic, that very first book by Caddy and then Tierson. So I would like to say that Tierson book is very famous when you are going to develop a mathematical models like I have developed for a shell. Similarly, that book was devoted on a linear piezoelectric plate vibrations. Then Zhou is a piezoelectric shell. So in that book the mathematical modeling of piezoelectric shell is explained, and recently that Uchino, Professor Kenji Uchino from Penn State University, I think he has developed a number of devices using the piezoelectric or their effects, and he has written I think more than 10 books that ferroelectric devices, their manufacturing behavior, and recently also in 2020 he has published number of lectures. So if we talk about the mathematical modeling, then Wu et al. 2008 paper is very much I would like to say that important paper in this field. So natural piezoelectric materials, as I have discussed, that tourmaline, quartz, topaz, cane sugar, which shows the effect, and then we have a ceramic materials, the most famous lead, zirconate, titanium, then potassium niobate, sodium, then zinc oxide. So these are the lead based piezoelectric materials. So recently because this cause environmental pollution, not good for health, so a concept of lead free piezo ceramics comes into the picture, and researchers have developed different materials like sodium potassium niobate, bismuth ferrite, or a barium titanate, bismuth titanate, and sodium bismuth titanate. So these are ceramic, and then the concept that because ceramics are brittle in nature, so for a flexible applications, if you want to study something for health applications, then you need a flexible membrane. So in that case polymers are also shows this effect. polyvinyl fluoride and its copolymers, polyamides are also showing the piezoelectric effects. So, in this way you can see that we have a 4 category of piezoelectric materials. One is the natural, another is the lead based ceramics, then lead free ceramics, then the polymers. If we look on the published paper in this field, if you see that in this field 26,000 articles are published on the plate, and you can see here that the top authors who are published in this field piezoelectrics like Yang, Zhao, Song, Wangzhe, Professor Kaporia. So, Professor Kaporia from IIT Delhi has developed or has worked on this field, and lot of number of articles have been published by him. So, we can see that as far as Chinese, USA and our Indian authors have worked in this field, and most of the application are the engineering applications, and the articles are I think more than now 27,000. So, these are only mathematical, means that mathematical modeling, not like manufacturing or fabrication, that is different area. Similarly, if we talk about that piezoelectric shells and shell application, in that Professor M.C. Ray, Zhao H.S., Professor M.C. Ray from IIT Kharagpur and Professor J.N. Reddy, Yang, Carreras all have developed that means mathematical models for the shell case, and around 10,000 articles. So, these are some analysis which I have taken from a Scopus, that okay, these number of papers are published in this field and these are the top authors who have published in this area. Why, what is the motto behind to show this slide? Just to know that okay, this field is very active, and this you can see on a graph it is increasing. So, it has started in 1985 or specifically 1980, 1991, and it is going up and up. Just you see that 2019 because of a COVID it has suddenly dropped, but obviously it will go up. Now, how this material have this effect? So, material had to be piezoelectric if application of an external mechanical stress gives rise to dielectric displacement in this, or it causes a electrical voltage. If you apply a voltmeter, so there will be in electrical voltage. Then there is a converse effect, sometimes it is known as reciprocal effect or inverse effect. If you apply a electrical field, then there will be a strain. So, for that purpose we will have a constitutive relations. So, if you talk about in a lead titanium oxide, in lead titanium oxide initially this happens due to that this is not symmetric, basically slightly stretched position, and then it causes a, it is not in center. So, when you apply a poling or you apply a stress, so dipole moment changes, and due to the net effect is that some charges are, means electrical voltage can be detected. Similarly, when you apply a electrical field, so then again a strain takes place in the crystal. So, this effect is explained here. So, the constitutive relations, I would like to just correlate something like if you talk about pure mechanical or let us say steel or a composite material, what is that? Sij(KL) into epsilon sigma KL, this we know, this is our, because of stress strains are generated if it is a elastic, pure elastic material. Now, it is having some piezoelectric effect. So, plus dNij into En, basically En is the electrical field, dNij is the piezoelectric constants. So, if you apply an electrical field and this constant, so strains will be developed. Let us say there will be no stresses, then it definitely then D33, if we talk about only single dimension, then E3, this converse effect will be there. Similarly, there is another equation that is sometimes it is denoted by Pn or sometimes it is by electrical displacement or electrical flux density. So, in this way if you say that some stress is applied, then electrical field will be generated. That sigma ij is stress, here d and ij is the piezoelectric constants. So, in this way our electrical field is coupled with the mechanical field. So, we have to solve these two equations together. So, we cannot solve just by this. So, we have to take care because the coupling takes place here sigma KL, sigma ij, En. So, you can say that this is a corresponding term, but it will be a electrical flux density or electrical. Then again in a general sense, here I would like to tell you that these variables can be written in different ways. For example, if you talk about an elastic material, that sometimes we say na, stress is directly proportional to strain. If you talk about a generalized Hooke's law, it will be C times or whatever into epsilon, and converse of this epsilon equal to S times of sigma. This is for only two possibilities are available for the case of a elastic material. But now we have a 4 variable kind of things, like first we say that stresses are expressed in terms of strain and electrical displacement, then electrical field. So, now we have a 2 set of equations and 4 variables. So, basically we will have, here you have 2 variables. So, you will have 2 sets, either you express stresses in terms of a strain or strains in terms of a stresses. Here if independent variable, if strain and electrical displacements are independent variable, then stresses and electric fields are expressed like this. If you are saying stress and electric field is your variable, then strain and electrical displacement are expressed like this. Then you take sigma and d, then you take epsilon and d. So, in this way 4 combinations are available. So, depending upon requirement we may use any one of them. So, generally that small change in strain, if you check change in strain with respect to the stresses, similarly with respect to the electrical field, with respect to the temperature, yes, temperature also comes into the picture, that effect is also there, that is known as pyroelectric effect, that if you rise the temperature then there will be a stress, or if you having some electrical field then again there will be some stress will be generated. So, this is the mechanical coupling, this is the converse piezoelectric coupling, and this is the thermal expansion. Now, here you see that the concept of D is written here, means Y and D, and here E is written here. What is the meaning of that? It means with the constant electrical displacement, or with the constant electrical field, or with the constant stress, and sometimes with the constant strain. What does it mean? Means when you study, means find out electrical or mechanical properties. So, these mechanical properties changes with the sometimes electrical field. So, if I say that with a constant strain, this electrical field, means this property, this beta is obtained having the constant strain, or if we say that this Young's modulus is obtained by when we subject a sample under constant electrical displacement. If you come up here, that is capitally constant electrical field, when a sample is subjected to under a constant electrical field, and then you apply extension or something, and then Young's modulus will be slightly different. So, it is dependent upon D and E, or a sigma or epsilon. So, based on that, so basically when you talk about epsilon, then that will be dependent on the either E or either D, and then the E and D are depend either on sigma or strain. So, these are 2 important things, that these properties, either you talk about Young's modulus or you talk about the dielectric constant, they are dependent on stress or the electrical field. So, if you changes the electric field, you will get a slightly different value. The meaning is this. So, the detailed 3-dimensional constitutive relations are expressed here. So, you say that these are the strains, this you know, compliance matrix, stresses and piezoelectric constants, and then electrical field and thermal expansion, coefficient of thermal expansion, and theta is the temperature. Similarly, electrical displacement dx, dy, dz can be expressed, piezoelectric constant, stresses. These are known as relative permittivity or dielectric constants. And electrical field. Now, this is known as pyroelectric constant. Vice versa, if you want to know that stresses in terms of strains and electrical field, then electrical displacement in terms of strains and electrical field, you can use these things. So, here the relation can be find it out that it will be S inverse, or then it will have some more terms will be there, you can find it out all these things. These matrices are valid only for orthotropic materials. When we assume that material properties are orthotropic in nature. But if you say that it may be transversely isotropic or it may be some anisotropic, then wherever 0, then some more terms will come up. But till now, whatever we have used during the modeling, even that piezoelectric materials are transverse isotropic. So, basically that 1 and 2 direction or 1 and 3 directions properties remain same, and only second direction is different. Sometimes 1 is different and 2 and 3 are same, like our composite materials. So, piezoelectric properties are also following the same manner. So, we have now defined the constitutive relations for a piezoelectric materials where elastic, piezoelectric and thermal is expressed. As in the week 8, I have developed the 3-dimensional solution. So, here also I will explain the first that basics, that how do we develop a 3-dimensional solution for a piezoelectric shell. Then I will explain that means the basics of a 2-dimensional solutions. So, already we have explained that displacement based approach, stress based approach and mixed based approach. So, out of which Professor Kapuria has developed mixed based approach. So, I have going to follow this approach. This is the far better approach compared to these two approaches, because the accuracy of stresses as well as displacements are same level. Now, we see that let us assume a piezoelectric a cylindrical shell in which some of the layers are piezoelectric. Our concept is that hybrid shell means that some layers are made of composite materials and some layers are made of piezoelectric materials. Like most of the cases, generally the top layer or bottom layer are piezoelectric layers, but it may be in between. So, this formulation is very generalized that you may consider in between piezoelectric layers are also. U is the radial displacement, V is the circumferential displacement, W is the longitudinal displacement. The total thickness is H and theta ZR is the coordinate system. And this is the finite length cell. Already you are having some idea that in finite shell. So, and this is the geometry of a infinite length cell panel. So, infinite length panel, if you say that epsilon equal to S times of sigma plus D times of capital E. So, that I will explain later where this comes. So, basically the strains in the cylindrical coordinate system are expressed here directly, and these are the new terms which I have not explained till now, that is electrical displacement and then concept of stresses and the phi comma theta phi comma. So, you find you see a new variable phi. Before that, in that it was E1, E2 and E3. So, E1 was the electrical field along one direction, E2 is the electrical field along second direction, electrical field along third direction. So, electrical field, let us say E1 is phi comma, first direction is theta, theta z, let me see just back, theta z and r, yes. So, it will be minus phi comma of theta. E2 is minus of phi comma z. E3 is minus phi comma of r. This is like that. So, here phi is known as electrical voltage. So, basically if we talk about in a discrete sense, because we have written in a vector form, if you say it will be V by H, means the voltage across the thickness phi comma z, if we write in terms of a that d phi by dz. So, small change in voltage upon में small change in thickness. So, change in thickness. So, basically voltage across the thickness, if we do so, then it gives you a electrical field in that direction. So, here we are talking about D31, D32, D33. If you see this first equation D31, so first, second, 2, so basically third comes into the picture, E3. So, E3 is minus phi comma r. So, that is why it is written as phi comma r, where E2 phi comma theta and phi comma z. So, for the case of a infinite cell panel, the derivative with respect to z, which is the longitudinal axis, is eliminated here. You do not find that derivative of z is here. So, wherever a derivative z, here is clearly written w comma z, which is going to be 0 here. So, all the entities are independent of z and their derivatives are neglected. Then we use the concept of equation of momentum. So, these equations you are aware in the case of a cylindrical coordinate system, and this is our new equation, which is the charge balance equation. I am here going to just explain what are the new variables are here, and then this you know, sigma r minus p1 p2 and tau zr. So, these are new variables that at the top or bottom we can apply electrical field or electrical voltage or electrical displacements. Any one of this, either means here is a concept of open circuit and closed circuit. When we say closed circuit, it means electrical voltage is applied. It may be 0, it may be non-zero, that phi is applied. When we say open circuit, it means you cannot apply phi, it means their electrical displacement need to be specified, that is taken as 0. dr or dz. For a 3-dimensional solutions, we need to satisfy the interface continuity condition. So, these are our 3 displacements, 3 stresses. Now, 2 variables further comes into the picture, which is phi is electrical field and d is the electrical displacement, that need to be also continuous at the interfaces. So, basically these 2 variables come up when we have a interface of a piezo layer and let us say elastic layer, and this is our piezo. And similarly, maybe 2 layers also, or in between 2 piezo layer may be possible. So, at that interface. So, general solution can be written as for a simply supported case, and we have developed for a free vibration also. So, we will do that. In that case, u can be expressed in terms of a sin n pi xi. Xi is the non-dimensionalized coordinate along the theta directions. V can be explained similarly, phi and di can be explained in terms of a psi. So, this formulation is basically a coupled formulation where you are taking electrical field as a variable, means electrical voltage as a variable. But there are some formulations where electrical voltage is not taken as a variable, it is treating as a loading vector, like we are in the thermal case, that we do not solve that temperature, we take as a, let us say temperature is known to you and as a loading variable. So, in that case phi and dr will not be a variable. And then you know that governing equations can be expressed in a differential equations with varying coefficient, and previously we have 6 variables, now we have 8 variables. So, already the solution I have explained that we can explain the homogeneous solutions using the modified Frobenius series, and in the conventional Frobenius series instead of a E lambda zeta we have a R lambda. So, presently it is explains E lambda zeta, and if we substitute into this equation it becomes a eigenvalue equation and we solve in a recursive manner. So, basically zi plus 1, zi plus 2, 3, 4, 5 can be solved, and depending upon our accuracy or depending upon a required convergence we can say that how many terms we have to consider. So, we have obtained that in this kind of analysis not more than 20 terms. So, below the 20 terms the solution converges, convergence rate is very high and the solution can be written as. So, most of the cases for the case of a piezoelectric shells that roots are complex conjugate or the real, and the solutions, final solutions can be represented like here. So, here C1 and C2 are the arbitrary constants that can be found it out by satisfying the boundary conditions at the top and bottom. So, the detailed solution procedures you can find out in Kapuria's and Achari's paper, and in our paper also, that Kapuria and Kumari paper also, where we have solved a 3-dimensional solution of a infinite length shell. And I would like to say that some results are presented here. Let us say that how do you present your results. So, these are the configurations, let us say complete single layer of a piezoelectric shell, and then we may have a composite laminar having any kind of angle, and then symmetric layoff, and then the sandwich, the core is thicker, very less density than face, and PZT5 face symmetric panels. And similarly, we have a concept of here you see that PFRC. PFRC means the piezo fiber reinforced composites. I would like to explain here that the term PZT5H is a material which is a soft, known as soft piezoelectric materials, which is having high, very high D31, and PZT5A is known as a hard piezoelectric material. The monolithic layers, if we attach these layers to these composite laminates, so basically these are ceramic in nature and they crack very easily. So, a concept of piezo fiber reinforced composite where we mix some reinforcing means a matrix material and we prepare still this is not commercially available or very less work is done in this area. So, PFRC is still a concept, that piezo fiber reinforced composite, where we assume that similarly like glass fiber we have a piezoelectric fiber and epoxy matrix, so that we will have some flexible laminate so that there will be no cracking. But the concept is that in that only the actuation is less because the dielectric constant becomes low. These days researchers are working in this direction, that can we get high piezoelectric constant, so that same level of actuations can be obtained like PZT5 or PZT5H. So, these are the material properties. Here you see that Young's modulus materials, then core, then PZT5A contains 61 GPa, and you see that 1 and 2 material properties are same. So, it means the piezoelectric 5H materials are 1, 2 means transverse isosymmetric in one and second direction. Third direction is different, and these are the Young's modulus. The extra material properties are piezoelectric constants D31, D32, D332415. So, these are in terms of a picometer. So, basically 10 to the power minus 12, and then we have a piezoelectric, dielectric or relative permittivity. Sometimes it is known as relative permittivity. So, that is known as 15.3. It is having a means common is 10 raised to power minus 8, and this is the piezoelectric constant. They were having a unit 10 raised to power minus 12, and this you know in terms of a GPa. So, it will have 10 raised to power 9. So, we have developed that solution, and we have compared our results with the previous literature results, and it was found it was in good match for angle ply shell, and then we have developed a result for a having a piezoelectric shell in which open circuit at the outer panel and natural frequencies. So, basically when you have a closed circuit and open circuit, the frequencies changes. So, having a piezoelectric layer, and if you change the circuit conditions, electrical circuit condition, its natural frequencies changes. The message is this. So, and not very means you can say that D1 and D1 panel. So, open circuit and closed circuit. So, phi is 60 degree and phi is 120 degree. Then again I think open and closed circuit, yes, there is closed circuit conditions and open circuit conditions, frequencies changes. So, basically if you see engineering point of view, you say that its change is not much than the 10%, but it may affect the very sophisticated instrument. So, if you are design a instrument which is used to find out a very accurate measurement, then they play a major role in designing the equipments for a sophisticated applications. But in general, if I will say that, if you say that 0.87, 0.92 non-dimensionalized natural frequency, so there is not much difference. So, initially when you go for a higher mode, then you will find there will be not much difference. Then the effect of your length. So, if A by R, if you increasing, then this effect of changes. So, initially for the plane strain assumption. So, after 6, so if your length whatever is length is along this direction and the radius. So, if this is A by R is coming 6 aspect ratio, that means it is good. You can apply a plane strain assumptions. There will be not much difference between the natural frequencies. Either you do through a very accurate 3-dimensional formulation, or then using the plane strain assumptions. So, after the 6 it will give you the. So, basically when is a qualitative, like we cannot say that infinite length along the z direction. So, if you take our length is, if let us say if r is 1 and length is 10 along that 10 times of the radius, then it will be treated as a plane strain. So, infinity does not mean that in very infinite 100 or 20 for the case of a shell. It is if you have a less means more than 6, it comes into that category. So, at 10 it is perfectly same for the case of frequency. Similarly, the values across the thickness, how this displacement varies along the thickness. If you remember that in the case of first order shear deformation theory, we assume that our displacements varies across the thick linearly, but here you see that in the case of a piezoelectric shell, it depending upon the thickness, if it is thick, you see that how it is varying, it is completely non-linear or quadratic in nature. So, it is not a linearly varying. So, these 3-dimensional solutions help you tell you that okay, we have to, means for accurate prediction we have to go more terms. And similarly that W, you can see that linearly varying, but we take a constant for the case of 2-dimensional shell theories. So, if you assume a 2-dimensional theories, even for the case of a thin shell, which is the dotted one as 20, still it is not a straight, it is having some variation. So, by taking more terms in the UVW, we can get more accurate solutions, and then you see the behavior of stresses transverse shear stresses and the electrical displacement. Now we talk about two-dimensional shell theories, that what are the basics behind that. Generally the two-dimensional theories are divided into basically two main categories. One is the coupled, another is the uncoupled. If you see in the literature, most of the uncoupled theories are available. So in the uncoupled theories, phi is not taken as a variable. So for the case of a plane stress case, the reduced stiffness matrix, and this is our electrical piezoelectric constant. So these are the governing equations. So initially, if you remember, for the case of a elastic shell, I have discussed up to here, but if you want to analyze a piezoelectric, then you have to consider these terms. Similarly in the stresses, transverse shear stresses and our displacements. So this comes into the picture, and again for the case of a full orthotropic, obviously all terms come into the picture. Here I would like to explain that Professor Kapuria has developed that, can we assume phi electrical field. If you see, just let me go back, the variation, that this upper layer is our piezoelectric layer. So how it is varying? It is going linear, from let us say 0 to some value. So this variation we need to capture it. Then if we assume a constant, so it will not going to solve our purpose. So initially some different variable has been expressed, and after that I think Professor Kulkarni and Professor Kapuria, they have developed a quadratic means. Initially it is piecewise linear, let say in a layer it is linear, and next layer not a constant function is taken, linear function. So this function is a z phi j, so it changes from layer to layer. Let us say we what they actually did, that a piezoelectric layer is divided into some n mathematical layers. Actually it is one layer of a piezo, but mathematically it is divided into n sub layers, and each layer the variation goes like this, piecewise linear, so that we can capture the effect. So it has been found that if we consider only this variation, it does not give the accurate estimation. So we need to divide each piezoelectric layer into 4 subparts, 5 subparts. So later on Professor Kapuria has given this concept that a quadratic consideration can be taken as that linear plus this. So with this help, we are able to just with the help of a single, we need not to mathematically divide into sub layers, it will be a single layer, and having this concept we can, in a single layer we can get the accurate estimation. So in this way, that deflection having these terms. So this makes a major difference in the accuracy of a piezoelectric plates or a shell. Because of these terms we can get a accurate deflection as well as the other terms. So it also reflect, because of this it also comes into the displacement field also. So we have assumed that strain in a piezoelectric shell or panels or a plates heavily depend on D33 and phi comma z. So we can take contribution of this, and previously we have taken a w comma z is 0, but now we have assumed that w comma z is not 0, it is equal to minus D33 phi comma z, and it is substantially giving a significant contribution, and then because of this some new terms have come up, and the rest of the procedure is same. We have obtained the u and then strains. Then here is the principle of or Hamilton principle. So Hamilton principle, till you are aware that sigma ij into epsilon ij. So this is all 3 dimensional terms are there. So now we have to add extra terms, energy contribution, that is given in Thierston book piezoelectric medium, for that electrical field and electrical voltage. These three terms come into the picture, plus the contribution due to the external work done and external work done due to the electrical field. So, these some terms comes into the picture and equations becomes more complex, and it is known as a modified Hamilton principle for the case of a piezoelectric medium. So, if you want to do study for a piezoelectric medium, you have to consider these terms. So, these terms are given in Professor Kapuria's paper. You can go through, or any like piezoelectric book, the modified Hamilton principle. So, the as work, obviously some electrical work done will be. Now, I am going to more generalize. Let us say you want to study for a magnetic plate. So, you will include some magnetic energy also, by the same way. And then it is on area, and this small angle bracket is for minus h by 2 to plus h by 2. If you talk about a composite, then it will be zk plus 1, k goes from 1 to n or 1 to n. So, these are defined like this: strains F1, F2. So, F1, F2 is nothing but these are the stress resultants. So, in plane stress resultant, moment resultant, higher order moments, and some electrical field resultant. So, in this way some new definitions or terms need to be defined, whether it is electrical stress resultant, and similarly you say that Sij, X. So, these are the due to the electrical field. Similarly, the Q, shear stress is generated due to the electrical. Similarly, here Q tilde. So, these some new terms comes into the picture, and corresponding definition need to be find it out. So, one can go through these kind of formulation and can develop the governing equations for the case of the shell. So, I have tried to briefly explain that how to develop governing equations, or what are the basics basically behind the development. So, you have to systematically add your electrical terms. So, with this I hope that it will help you to develop for more advanced material, and you can go through. There are number of books, lot of papers are available on this piezoelectric shell, piezoelectric modeling. So, you can go through all these things. With this I would like to say thank you very much.